What is a capacitor? A capacitor is an electrical component with two terminals, kind of like the resistor. People commonly refer to capacitor as cap for short. Caps are components that are particular differently from resistors that don't store any energy. Capacitors are able to store electrical energy, and you can think of them sort of as little batteries. Capacitors are used as energy storage. They're used for signal filtering and also to suppress voltage spike. In this lesson, we are going to discover how capacitors are made, what's the fundamental structure, and how they work. So first of all, let's focus our attention on the left of the slide, when we have a sketch of a parallel plate capacitor. This is the way capacitors are usually introduced, like in school, because it's the easy way to understand how the capacitor work and what are the fundamental components of its structure. Though obviously commercial capacitors you can buy, they're not fabricated this way, but this is nonetheless a good way to introduce the component. As you can see, it looks like sort of a sandwich. There are three main components. So two of them are on the top and the bottom, and they are metallic plates. So you can think about this as really two pieces of metal, flat as a plate in this case, that are able to conduct electricity. And then in the middle of the sandwich, we have a material here represented in gray, which is an insulator. So this material actually does not allow the current to go through the device. And this material is called dielectric. And you can have different materials there, and different material will be characterized by different constant, which is epsilon r. And the epsilon r indicate the relative permittivity of the material. Now, as we will see later, depending on the geometry of the plates, the distance of the plates, and the epsilon r, the relative permittivity of the material, you will get different value for the capacitor. On the right of the slide, we now go ahead to explain how the capacitor actually work. So there is a little circuit here, so let me introduce the circuit first. So we recognize different elements. So this one is the voltage generator. Again, this could be just a battery. That's probably the easiest way to think about it. But ultimately, this could also be there are instruments that you can buy and just give you a certain voltage. Then we have a switch here. And then on the right, we have a stylized version of the parallel plate capacitor that we just talked about. Actually, this is exactly the way the capacitor is represented in circuits. So we'll see that later a little bit better, but capacitors usually are represented in circuits just like this. So exactly to remind you the example of the parallel plate capacitor and to remind you the way the component actually works. Let's now see what happens when we close the switch. So we close the switch. So now the two part of the two components of the circuit, which is the battery and the capacitor, are now going to be in parallel, as you can easily tell. Hence, they'll be subject to the same voltage. So whatever is the voltage of the battery, you are applying that voltage to the capacitor. As we discussed before, the capacitor is made of two parallel plates, which are made of metallic material. You can think as if they are made with the same type of material of the wire. So just like a strange looking wire. But in the middle, there is a material that is an insulator. So it's kind of intuitive to think that, okay, maybe something will happen just the instant after you close the switch. There will be some current, some readjustment of charge and voltage. But then eventually, the current through the circuit has to be zero. Because as just I'm indicating with the symbol of the capacitor, there's really no direct connection between the upper and the lower part of the circuit. And that is in fact true. So when you have a constant voltage applied to a capacitor, eventually the current becomes zero. This may seem a little bit strange, but actually capacitor can still be very, very, very useful as an energy storage device, as we'll see later. So what happens is that a certain amount of positive charge is accumulated on the plate, on the upper plate, and a certain amount of negative charge is accumulated on the lower plate. Keep in mind that usually the distance between the two plates, now here is highly exaggerated just to make a point, but usually it's really, really, really small. So yes, the circuit is open, there's no direct connection between the two parts of the circuits, the two terminals of the battery, but these two plates are really, really close to each other. So positive charges and negative charges are not allowed to cross the capacitor to go on the other side, but they definitely see each other really well. And because positive and negative charges want to attract each other, we're going to have a significant electric field inside of the capacitor, just as I'm indicating here. The The slides contain the two fundamental equations of the capacitor. So the first is this, very important. So this equation is a relationship between the amount of charge that a capacitor stores on its plates, the value of the voltage applied to the capacitor, and a parameter that is called C, which is the capacitance of the device. So obviously, a component called capacitor is characterized by a fundamental parameter, which is its capacitance. Now, this equation tells us that the amount of charge that can be stored on the plate is directly proportional to the capacitance and the voltage applied to the capacitor itself. The second equation that we want to discuss is down here, and this equation defines the value of the capacitance for a capacitor of a certain geometry and made of certain materials. The formula says that the capacitance C is equal to epsilon 0 multiplied by epsilon r, where epsilon r is a relative permittivity, whereas epsilon 0 is the permittivity of vacuum. So these are just constant. Epsilon r depends on the material that you use to make the dielectric, and then it's multiplied by A, which is the area of the metallic plate, and D is the distance between the metallic plates. So in this case, D will be the distance between these two plates, and A will be the area. The unit of measurement of capacitance is the farad, which is indicated with a capital F. 1 farad is a pretty big amount of capacitance. You will almost never find a capacitor with capacitance equal to 1 farad. So most of the time, the value of the capacitance will be in the range of microfarad, nanofarad, or picofarad. The equations that we just discovered tell us a very important thing. So the first up here tells us that the amount of charge that is stored in a capacitor for a given voltage depends on the capacitance. The other equation down here tells us that the capacitance in turn depends on the geometry of the capacitor and the material used to build the capacitor. So if you put these two concepts together, the result is that the charge that can be accumulated, that can be stored on a capacitor for a given voltage, depends on the geometry of the capacitor and the material used to build it. The goal of this lesson is to give an intuitive understanding of why that is the case. Two are the things that you have to keep in mind to understand this, and are very simple. The first is that charges with different sign attract each other, and the second is that charges with the same sign repel each other. The battery here, you can imagine it as an unlimited supply of positive and negative charges. So what we're trying to understand here is why, after all is said and done, only 4 positive charges and 4 negative charges are sitting on the plates. Why not 5? Why not 6? Well, in order to understand that, we'll imagine to be in the mind of a positive charge sitting there and trying to decide whether to go in the capacitor or to stay in the battery. So 2 thoughts will go through the charge's mind. So the first is that the charge really wants to go on the capacitor plate because it really wants to reach the other side of the battery. It really wants to reach and recombine with negative charges. At the same time though, in order to do that, that charge will have to go on the plate, which is full of positive charges. We know the charges of the same sign repel each other, so that's one reason why that charge might not want to go on the capacitor plate. This trade-off between wanting to go on the plate and not really wanting to go there goes through, if you want, every charge's mind. But in the end, an equilibrium is reached and a certain amount of charge is allowed to be on the plate. It's now easy to see why the geometry of the capacitor and the material used for the dielectric changes the equilibrium point that determines the number of charges accumulated on the plates. Let's start with the first element here, which is probably the simplest one to describe, is the distance. So if I change the distance between these two plates, now for this charge sitting here, there is a much stronger incentive to go on the plate, because yes, there are still positive charges there, but there's still just 4 of them, and now the negative charges are much closer. So there is a stronger incentive to go on the plate. Of course, after the 5th charge has gone on the plate, a new charge, a 6th charge that wanted to go on the plate, will have to take into account that now for the given distance, now there are 5 positive charges on the plate. So it is possible that the 6th charge decides not to go in the capacitor after all. Let's now consider the effect of the area on the amount of charge accumulated on the capacitor. Well, the area works in a different way than the distance, in the opposite way actually. So it's a bigger area that gives you a higher amount of charge in the capacitor. The reason for that is intuitive and simple. So if we increase the size of this plate, the area of the plate, now for the same distance between the positive charges and the negative charges, now the positive charge sitting here and trying to decide what to do, we'll see that after all going on the plate is not as bad because the density of positive charges is not so high. So yes, there will be 4 charges, but that new charge will be able to carve a larger space for itself. So the charge eventually decided to go on the plate. Now again, a 6th charge wanted to do the same. We'll have to consider that the real estate available has been decreased because a 5th charge went there, and so on. Last but not least, let's describe the effect of the dielectric material here, epsilon r. The dielectric material is put in between the 2 plates. So for a certain fixed distance between the plates and a certain area of the plates, if you change the dielectric, you can change the amount of charge that will be willing to be stored. The reason for that is that the dielectric can make it easier or more difficult for the positive and negative charges to see each other. So if you choose a dielectric that make it easier, more charges will be stored in the capacitor. If you choose a dielectric that make it more difficult for charges to see each other, there will be a much lower incentive for charges to cram themselves in the plates, and as a result, a lower amount of charge will be stored. Another thing worth noting is that a capacitor always has the same amount of positive and negative charges. As you can see here, for each negative charge on the lower plate, you have a positive charge in the upper plate. Each positive charge in the upper plate is neutralizing the effect of one negative charge in the lower plate, so that a new positive charge doesn't have an incentive to go on the plate. If you had a much higher number of negative charges than positive charges, then other positive charges will want to go on the plate because they will be able to see the negative charges through the positive charges. But the moment that you have the same amount of positive and negative charges, the capacitor becomes neutral in a way, so a new charge will not have an incentive to go on the plate. So at the equilibrium, the number of positive charge and negative charges is always the same. To summarize what we have learned so far, the simplest representation of a capacitor is made by an insulating material that is called dielectric. And this material is sandwiched between 2 metallic, so conductive plates. One on the top, upper plate, and the lower plate. The capacitance of a capacitor, which is the main parameter of this component, represents the amount of charge collected on one plate for a given voltage. So if you apply a certain voltage V across the component, you will accumulate a certain amount of charge plus Q on one of the plate and minus Q on the other plate. The capacitance, which is indicated with C, remember that Q is equal to C multiplied by V. The capacitance C is measured in farad, but as I already said before, farad is a really big amount for capacitance. So most likely you will see values of capacitance expressed with different submultiple of the farad. For example, with typical scientific notation, microfarad, nanofarad, and picofarad, where each of these unit of measurements means that you have 10 to the minus 6 farad, 10 to the minus 9 farad, and 10 to the minus 12. So for example, if someone gives you a capacitor that has a capacitance of 1 microfarad, you would know that the amount of capacitance of this capacitor is 1 over 1 millionth farad. In this lesson, we're going to discuss why a capacitor is an energy storage device, and we're going to try to provide an intuitive explanation of why that is the case, though we're not going to go into complex physical calculation or demonstrations. On the left, we have our usual parallel plate capacitor. As you can see, we have the 2 parallel plates, metallic plates, we have a dielectric. We apply the voltage across the 2 terminals, and we know that when that happens, that means that we have a certain amount of positive charge accumulated into the upper plate and a certain amount of negative charge on the lower plate. And the presence of this accumulation of charge, or positive and negative charge, generates an electric field within the dielectric. We also know that the amount of charge that is accumulated on the capacitor depends on the voltage and also on the value of the capacitance of the device, which in turn depends on the geometry of the device and the dielectric, accordingly to this equation, Q equal to C multiplied by V. Let's talk about the energy storage aspect of a capacitor. So let's say we have this capacitor on the left that is biased at 3 volts, which means V is equal to 3 volts. For example, we can say this terminal is a ground, so 0 volt, and this terminal is at 3 volts. Now, if we remember the definition of volt, we know that volt is electric potential energy per unit of charge. Well, now if we look at this drawing, we see that we have a certain amount of positive charge Q that is sitting there at 3 volt potential. So if volt is electric potential energy per unit of charge, and we have a certain amount of charge sitting there at that potential, at that voltage, that means that the capacitor in a way is storing a certain amount of electric potential energy. Now, if we look at the second bullet, we also remember that Q, the amount of charge, is also directly proportional to the capacitance. So for the same amount of voltage that you apply to the capacitor, if you double the value of the capacitor, you double the amount of charge that is stored in the plate, which in turn means that you are doubling the amount of energy that is stored by the capacitor. So in a way, we can say that the capacitor is an energy storage device. So if you have a capacitor and you apply a certain voltage, that means you are storing in the capacitor a certain amount of energy. The bigger the capacitor, the bigger the energy for the same voltage, and vice versa. If you now want to quantify the amount of energy, that is not a very easy feat. In order to do that, you actually have to do a more complex calculation that involves integral. I give you the short version of it, or rather I just give you the solution. So if we look at the last bullet here, that shows us what is the electric potential energy that is stored on the capacitor for a certain given amount of voltage and a certain amount of capacitance. So the value of the energy is 0.5 multiplied by C and multiplied by the square of V. So actually the energy stored in the capacitor highly depends on the voltage. So the voltage goes with the square. So if you double the voltage, you actually quadruple the amount of energy. And it goes linear with the capacitance, as we said before. So if you double the value of the capacitance, you double the amount of energy. Before moving on, I want to make an important point about the capacitor that is illustrated in bullet 3. So we said that capacitors store energy, and that is true. The capacitors store energy in the electric field, and despite the fact that my explanation was everything but accurate physically, the concept is real and the equation I provided for the energy is correct mathematically. Now, you also heard me say many times that the capacitors store charge. But if you think about it, that is not really true. Just look at the drawing that I have on the left. Does it look like the capacitor is storing charge? I don't think so. Think about it. Like, all I'm saying here is that when I apply a certain positive voltage, I have a certain plus Q on the upper plate and a certain minus Q, a negative charge on the negative plate. So if that is the case, this doesn't really match very much with the dictionary definition of storing something. I have a plus something on one plate and minus something on the other plate. So when I consider the capacitor as a whole, there's really no net charge that's being stored. Plus Q and minus Q will simplify each other. So at the end of the day, you could say that the net amount of charge is always the same. So what's going on here? Well, what's going on is this. So remember, we don't really have positive charge in circuits. It's all about electrons moving around. So when you apply a certain voltage to a capacitor, what's happening is that a certain amount of electrons are accumulating to the lower plate. So they are adding to the already present electrons in the plate. And the same amount of electrons are fleeing the upper plate. So remember, the plates are metallic, so they have their natural amount of electrons there. And when you apply a voltage, all you're doing is that you're adding some electron to the lower plate. So you end up with more electrons. And you remove some electron from the upper plate. So that is what's happening. So in effect, there is no storage of charge, because you increase the charge on one plate, but you decrease the charge on the other plate. The human brain doesn't deal well with the absence of object. So it's very non-intuitive to say that you have a positive charge plus Q on the upper plate, because you have a lower number of negative charges accumulated there, and a lower number of electrons. It's much simpler to believe that a positive imaginary charge exists, and when you say that I have a amount of positive charge accumulated on a plate, it means that these positive charges somehow got accumulated there. Similarly to what happens to the lower plate for electrons. Different being that for the lower plate that is true, for the upper plate that is just a trick, something that we imagine to make the analysis of the capacitor easier. Another reason why using positive charges is useful is that positive charges move in the same direction of the current, and the human brain really wants to make analogies to understand events. So in the case of the current, it's very easy to make an analogy between a stream of water and the current. In the stream of water, you know that the stream is going in that direction, the flow is going in that direction, because a bunch of molecules of water are going in that direction. And it's easy to believe the same for the current as well. So the current is going in that direction, there must be something moving in that direction. So that's why using positive charge is something that is down all the time, but you have to keep in mind that usually whenever I plus Q, it really means that you have a lower number of electrons there than you would usually have if there was no voltage applied. To summarize again, the capacitor in effect does not store any charge, but it simply changes the distribution of the same amount of electrons between the two plates. So one plate ends up having a higher amount of electrons, the lower plate. The other plate ends up having a lower amount of electrons. In this lesson, we're going to talk about the symbol used to represent the capacitor in a schematic. I already used a symbol before, I've used this one. And as you can see, it represents really well how a parallel plate capacitor is built. In general, it represents how capacitors are built. They're made of two plates separated by an insulator, and this symbol is very good at reminding you that. Now here I represent the 5 different options for the symbol that you can use. In most cases, the difference between, for example, this symbol and this symbol or this symbol is simply depends on a style choice for your design. And sometimes the difference is also geographical difference, like some symbols are more used in US, others are more used in Europe, but as you can tell, there is no fundamental difference between these symbols. They all represent the same component. The only two symbols that are really significantly different are these two in the middle. The symbol contains a plus sign here, and in the case of this one, we also have one of the two plates has a different color, a different filling. So in this case, the plus is not me trying to represent a positive charge accumulated, but this symbol is meant to indicate that the component needs to be mounted with a certain orientation, meaning that the way this capacitor is fabricated is such as the voltage at these terminals always needs to be higher than the voltage in the other terminal. So when you eventually put in your circuit, you have to make sure that the voltage in your circuit is always applies in this direction, and it's never applied with the opposite orientation. So the terminal on the top in this drawing always has to have a higher potential than the one at the bottom. Otherwise, if you don't do that, the capacitor could actually explode. It will definitely be damaged. These components are called polarized. And again, all it means is that they have a certain orientation. Once they are placed in the circuit and once they are in operation, they behave just like any other capacitor, but you just have to be extra careful to make sure that the orientation is the correct one to prevent any damage. In order to understand better how a capacitor works, and in order to have a better intuitive understanding, I'm going to resort again to a water analogy. So you see here on the left we have an hydraulic equivalent of a circuit. Which circuit? Well, it's very simple. There is a voltage generator represented by the pump, there is a resistor, and then there is a capacitor. So C, R, and V. So we have already seen that the pump role in these circuits is to generate a differential pressure between the intake and the outtake. So all the pump is doing is to generate a certain delta P that for us is a representation of a delta voltage. Now the resistor, we know it's an element that opposes to the passage of a current. So in the case of a hydraulic example is the passage of a water. So it can be represented as a choke into the tube that connects the pump and the capacitor. And the capacitor instead can be represented as a water tank split in half by an elastic membrane. So as you can see here, there is a membrane in the middle. This membrane is elastic, so it can be bent by a difference of pressure between the two chambers of the tank. but it's watertight. So it's not possible for any water to actually go through. But again, it's elastic, so if there is a difference of pressure between the two parts of the tank, it will be able to bend. A final thing that I want to highlight is that the two chambers of the tank, they have each one of them has a certain volume. So that means they can store a certain amount of water that for us is a representation of the charge. Before considering what happens when we turn on the pump, let's assume that the pump is off at first, and let's establish what's the value of the important parameters of the circuit. So in particular, for an electric circuit, we want to know what's the value of the voltage at every node and what is the value of the current in the circuit. In this case, this is an hydraulic example, so we know that the voltage is represented by the pressure and the current is represented by the water flow. So let's try to define those. So the bottom part of the circuit is equipotential, equipressure. So they're gonna have a certain value, and let's assume that the value of the pressure is equal to 0. Again, in electronic circuits, what really matters is the difference in pressure. So the fact that we assign the value 0 for the lower part of the circuit does not make any difference. It's just a convenient starting value. The pressure on the top part of the circuit will be different on the left and on the right side of the resistor in general. So we are gonna distinguish those two areas, and we are gonna draw two little graphs because we expect the pressure to evolve with the time after we turn on the pump. So we'll have these two little graphs, and at time equal to 0, which is what we are considering now, time equal to 0, the pressure is equal to 0 on both sides of the resistor. This means that the current going through the resistor is 0. There's no incentive for the water to go to the left or to the right side of the resistor because the pressure is the same. But another important consequence is the following. If we look at the capacitor, what we're saying is that the difference in pressure here is equal to 0. Now, pressure is a representation of a force over an area. So because the area is the same of the membrane on the two sides, the force applied in this direction and the force applied in this direction will be the same. So the membrane will just stay in the middle of the capacitor completely relaxed. This means that the two halves, the two chambers of the capacitor, will store the same amount of water. For us, the amount of water in the two chambers of the capacitor, it's a representation of the amount of charge stored by each of the plate, and in particular, it's a representation of the amount of electrons. Let's say we are now at time equal to 1, could be 1 second, 1 minute, and at this time we turn on the pump. So the pump is now on. This specific pump was designed to generate a delta pressure equal to V. I call it V because we already know the delta pressure is a representation of the voltage. So now, if we look at the pressure on the left of the resistor, we know that at time 1 the pressure went from 0 to a value equal to V. And from that moment on, the pressure will always be equal to V until we turn off the pump, because that is exactly how the pump is designed, fixed difference in pressure. We want to know what happens to the right of the resistor and specifically on at the capacitor. So at time equal to 1, the pressure in the capacitor will still be equal to 0. Because in order to have an increase in pressure there, we need to have a certain amount of water be added to the capacitor, to the upper chamber of the capacitor, and you need at least a certain amount of time to fill it with some water. So at time 1, you just turn on the pump, still the pressure in the capacitor is equal to 0. If the pressure is equal to 0 in the capacitor, now we can see that we have a difference in pressure across the resistor. So if we measure it like this, we have a difference in pressure that is exactly equal to delta P, which in our case is equal to V, because we have a pressure equal to V on the left and a pressure equal to 0 on the right, so the difference in pressure is equal to V. That means that we're going to have a current going through the resistor, or a water flow through the resistor, and this current is going to be equal to V divided by R accordingly to the Ohm's law. As the water keeps flowing from the left of the resistor to the right, water gets accumulated in the in the upper chamber of the capacitor. Remember that the membrane is watertight, so it's not possible for the water to actually circulate in the circuit, but the upper chamber will start getting filled with more and more water. So because there's no possibility of water to flow through the membrane, that means that the pressure on the upper chamber of the capacitor starts increasing, just like this. Pressure is force over area. So if we look at the chamber now, the bottom part of the chamber, the bottom chamber, has a pressure equal to 0. So the force, now here if you change it, that means that the force is equal to pressure multiplied by area. So in that case, the force will be equal to 0. So we have a force up here equal to 0. On the other side, on the top, on the upper chamber of the capacitor, we have a certain amount of water. The pressure is not 0 anymore. So we have a force that is bigger than 0. So that means that there is a net force that is applied to the membrane, and as a result, the membrane will start to bend. So if I delete it here and I represent with the dashed line the original position on the membrane, we'll see that the membrane start getting the form more and more as the pressure keep increasing. Now the question is this trend going to keep going forever? Is the pressure going to keep increasing in the capacitor and the membrane will keep deforming and deforming forever? It's easy to understand how this cannot go on forever, because otherwise the membrane at some point will break. Inevitably, it cannot be able to sustain an infinite force. So in order to understand what's happening, we have to look at the graph that we are drawing a little bit better. So we had initially a pressure equal to V on the left side of the resistor and a pressure equal to 0 on the right side of the resistor. And for that reason, we said that the current was going to be equal to V divided by R. That was true, but if you think about it, that was true only at the very beginning. Only at time equal to 1, the pressure was exactly equal to V and the current was equal to V divided by R. As the pressure built up on the left side of the resistor, the current will have to decrease. So let's try to do a little bit drawing here to represent this. Instead of having this fixed value for the delta pressure, I'm just gonna introduce another graph. So this graph represents the delta pressure across the resistor. At the beginning, actually at the beginning it was equal to 0. At time equal to 0, it was 0. And then at time equal to 1, it became equal to V. All of a sudden it jumped up. But now, as you can see here, the pressure is increasing on the other side, so the delta pressure is slowly going down. And because the current is equal to the delta pressure divided by R, that means that also the current it's decreasing with exactly the same waveform, with exactly the same behavior. This means that the rate at which the upper chamber of the capacitor is filling up is decreasing as the time goes on. So initially it fills up very quickly, but later the flow of water starts decreasing, so the amount by which the membrane gets stretched becomes smaller and smaller. If you let a long amount of time pass, the final state, the final equilibrium state at which you will find the circuit is the following. So the pressure across the capacitor, or the pressure in the upper chamber, would have reached the same value of the pressure that is applied on the left side of the resistor, so it will be equal to V, the same pressure value as the pump. For that reason, the delta pressure on the resistor would have reached 0, and same will happen for the current. So there will be no current anymore going across the resistor, because again, the pressure across the resistor is the same. The membrane will be deformed to the maximum extent, and it will stop moving. The water analogy for a capacitor allows us to see how a capacitor is a device able to store energy, and it also allows us to see once more that a capacitor is not, despite what people say when they use it, and despite what I say when I use it, when I refer to it, a capacitor is not a device that stores charge. We have seen with the exercise that after a pump is turned on, a certain different pressure is applied, and if you wait a long enough time, you are gonna have a different pressure applied across the two chambers of the capacitor. So you end up with the delta pressure here that is equal to V, is equal to the same delta pressure applied by the pump. So the difference in pressure means the difference of force applied to the membrane. So the membrane that is watertight, but it's elastic, will bend. The energy that we know a capacitor is storing in the electric field is represented in this water analogy by the elastic membrane being bent, because any elastic material, when it's in non-relaxed state, is in effect storing energy in a form of elastic potential energy, because you know that if you release the force on that device, the device will snap back, so it is able to produce a certain amount of work. So this membrane that is in a stress condition, it is bent, is storing energy as elastic potential energy. Regarding the charge, it's easy to see from this water analogy that whatever charge entered the upper chamber, the same amount of charge have to have left the second chamber, because the membrane is completely watertight you simply move the membrane. So the same amount of water that entered the membrane from the top left the bottom of the capacitor. So this is equivalent to say that when we say that a capacitor has a certain amount of charge Q, all we are saying is that we have an additional amount of electrons accumulated on the negative plate, and the same amount of electron has left the positive plate. Let's now see with a slightly better example how the capacitor stores energy with this water analogy. So as you can see on the slide, we got two capacitors there. I isolated the capacitor from the rest of the circuit. Same as before, let's assume that the pressure down here is equal to 0. And this is, the atmospheric pressure, for example. So the pressure is equal to 0 everywhere outside, like in this page. The lower part of the capacitor is open, so the pressure is equal to the ambient. Now we have these two capacitors, and we assume two examples. So one case is we have the capacitor with the membrane at rest, and so that means that the pressure inside is equal to 0. In the other case, the pressure inside is bigger than 0. And as you can see here, I draw a little door there. So in a way, you close the upper chamber of the capacitor so that the pressure can be kept there. And of course, we're assuming that there is a bunch of water here, for an example. Well, I don't think I need to provide much more explanation than this one. Everybody will realize that there's a very big difference of the behavior of the capacitor when we let the door open. So in one case, in the case on the left, when we let the door open, as I indicated here, let me delete and redraw this, open, so now it's open. Nothing really is going to happen. The water is going to stay inside the capacitor because there is the same pressure outside, inside. It's really like a smooth event, nothing really is happening. Like in this other case though, that makes a big difference. Like when the door is open like this, the pressure inside is higher than the pressure outside. A bunch of water will just come out of this capacitor. So that hopefully should give you a better understanding of why elastic material that is in a stress state is storing energy. This energy is elastic potential energy. Generally speaking, as you know, energy is generated and stored every time you somehow fix the setup, fix the system in a way where it doesn't really want to stay. Like in this case, the membrane wants to be relaxed, it doesn't want to be stressed, but somehow you build around it a setup that keeps the membrane in that state. In this case, you put the water and you close the cap of the capacitor, you close the door, but then you see that the moment that you open, that energy will be released and a certain amount of work will be accomplished. In this case, the work is accomplished to move the water out of the capacitor. So I hope this example helped clarify a little bit. In this lesson, I want to talk about AC current in a capacitor. First, let's start with some definitions. So here you can see the definition of DC current or direct current. DC current is a current where the electric charge always flows in the same direction. So for example, this is a possible representation of a DC current. So it's a current that always have the same sign, basically. So all the currents that we've seen so far were of this type. We had a battery. The battery is also a DC voltage, so called because the voltage also never changes sign. And then you connect it to the circuit, you wait some time, and eventually, let's say if you have a resistor, you have a current that is constant and always in the same direction. On the contrary, AC currents, or alternating current, as the name suggests, is a current where the electric charge changes direction periodically. So for example, electric AC current is a current whose behavior is like this. So it changes sinusoidally from a value, a positive value, to a negative value, which means that the charge is moving back and forth in your circuit. Before talking about alternating current, let's refresh our memory with studying what happens in this circuit for DC current. So I forgot the membrane here. So DC current is a current that is always going in the same direction. For example, a constant current like this one. Now this current is always positive, which means that you have a certain amount of water, in this water example, going in this direction. Now this water has nowhere else to go than inside the capacitor. And inside the capacitor, unfortunately, there is a membrane that is watertight, so the water doesn't have any other thing to do than just accumulate into the upper chamber. Now, in order to allow for additional water, we have already seen that the membrane will have to deform. And if we are forcing a current that has this shape, that is constant and it's forever a positive value for the current, that means the membrane will have to continue stretch Now it's easy to see how this is not possible to sustain indefinitely, and eventually the membrane will break. And this is exactly what happens also in the electric circuits. If you try to force a DC current into a capacitor, the voltage across the capacitor will keep increasing, and eventually you'll break the device. Let's now move on to the alternating AC current case. So let's say you have a current here that, because you have a special pump, this current behaves like this. So it keeps doing like this. So you have an I peak, and then you have a minus I peak. So the current keeps changing in a sinusoidal way. So it keeps changing direction with the time in a periodic fashion. So if you look at the water in a section of the tube, the water keeps going back and forth, back and forth, back and forth. What does this mean for the capacitor? Well, if you look at the membrane, when the water is going down, so it's going, the current is positive, so the water is getting accumulated in the upper chamber. So the membrane will stretch like this. Whereas in the second part of the period, the current is actually going up. So we are actually taking water out of the upper chamber and injecting water in the lower chamber. So now the membrane will stretch this way. So with alternating current, the membrane will keep just being bent up and down, up and down. There is no net accumulation of water in either of the chambers. And as you can clearly, intuitively understand, this is a situation where we can keep operating the capacitor indefinitely. In conclusion, we can say that capacitor block DC currents but allow AC currents. So it is possible to have to sustain indefinitely a current through a capacitor as long as this current is alternating. So as long as the direction of the current is periodically alternating, so that there's no net accumulation of charge or any of the plate of the capacitor. So remember not to get fooled. The concept of current is purely related to the movement of charges. It doesn't require that the charge starts from one side of the pump and goes all over around the circuit to the other side. Because if that was the case, then you couldn't have any current with a capacitor, because you have a watertight membrane that would not allow a charge to complete the whole loop. The current has everything to do with the movement of charges. So that if you sit in any section of the circuit and you just look at this section, no matter how the rest of the circuit look, if you see some charges moving in a direction or another, you can say that there is a current. That is why capacitor, despite the fact that technically leaves the circuit open, still allows a certain current. What the capacitor does, in a way, it doesn't technically close the circuit, but it allows the two parts of the circuit to feel each other through an elastic membrane. So it allows the two parts of the circuit to influence each other based on a difference of pressure in this hydraulic example, or a difference of voltage. Just as we did for resistors, we now want to talk about capacitor in series and in parallel, and we want to be able to calculate the equivalent series and parallel capacitance. Now let's start with capacitor in series. So we see here we have a capacitor. So I want to remind you that Q is equal to C multiplied by V, which means the capacitance is that property that defines how much charge is accumulated on the plates of the device for a given voltage. And we're going to use this relationship at our advantage to understand how we calculate the equivalent series capacitor. To make it even extra simple, as you can see here, I indicated the charge with little plus and minus sign. And usually this is just an indication of the fact that you have positive charge on the top plates and negative charge on the bottom plate. But in this case, we'll consider that as also an indication of the amount of charge. So in this case, we can say that we have 4 plus sign and 4 minus signs. And that is kind of an indication of the amount of charge on the plate of the capacitor. Let's now look at the circuit in the middle. So we have two capacitors in series. And these two capacitors in series, you can tell they're in series because they will be crossed by the same current, if there was one. And you can also notice that each of these two capacitors are identical to the original capacitor on the left, meaning that they both have a capacitance value equal to C. And for this reason, when there is a voltage V across them, you have a certain amount of charge Q. One thing it's really important to remember, and the peculiar thing that happens in the middle, it's kind of the important concept here. So here you see there are some negative charges, 4 negative charges and 4 positive charges on two different plates, but these plates now are connected electrically by a wire. So there's actually a path for these charges to see each other, to reach each other. And as we certainly know, positive and negative charges attract each other. So these charges will eventually just recombine. Also remember, when we indicate minus and plus charges, we really mean, with minus charges, we mean we have an excess of electrons, whereas with plus charges, we just mean that we have a defect of electrons, so we have less electrons. So overall, if you consider this piece of metal with this shape, so it's shaped like an eye, but eventually this is like just one piece of metal, you can consider that this piece of metal is electrically neutral because it has the same amount of positive and negative charges. So now, if you think about it in this term, that means that effectively, if we now want to jump to the right here and try to find the equivalent capacitor, effectively we have that these two devices in series, they are equivalent to one capacitor, which has a voltage equal to 2V across it, because you see it, we have one V and another V, so it's equivalent to 2 times the voltage. But the effective charge that is stored is only 4 plus sign and 4 minus signs, because the one in the middle got simplified away. So at the end of the day, if you look at if you want to calculate the equivalent series capacitor, for this case, the equivalent series capacitor would be equal to C divided by 2. So actually, when you put two capacitors in series, the effective equivalent capacitor is smaller than the initial capacitance, and we understood that by doing this, by looking at this simple example where the charges in the middle plates and the plates that get connected to each other get simplified away. So for a higher voltage now, you actually store a smaller amount of charge. So the equivalent capacitance becomes smaller. So if we want to extend the concept, again, because the example that we've seen before just assume two capacitors in series and they have the same value, but that obviously it's not always the case. And now in these slides, I'm showing what is the universal formula that you can use to calculate the series equivalent for a capacitor. And you will certainly remember that this formula is very similar to the one for the parallel resistor. So the equivalent series capacitor is equal to the inverse of the sum of the inverse of each individual capacitor that is in series. So in generally speaking, the series capacitor of n capacitor is always smaller than the smallest of the capacitors that you put in series. Calculating the equivalent parallel capacitance of two capacitors in parallel, it's even easier than the series one. So now we look at the left here, we have two capacitors identical in parallel. You can tell that they're in parallel because the two terminals are shorted with each other and because they will be subject by the same voltage. And these capacitors are the same as we've seen before, so they have for a voltage V across their terminal, they store a value of charge equal to Q, and we are representing this Q with 4 plus sign and 4 minus sign. If you just want to represent this with one capacitor, that is very simple and intuitive. All you have to do is that will be a device with a voltage across it equal to V because they are in parallel. But now this device, because you have the top plates and the bottom plate shorted together, you effectively can consider that as a single capacitor where the amount of charge that is stored is twice as much as before. So you have 8 plus sign and 8 minus sign. So in this case, the equivalent parallel capacitor will be equal to 2 times C. In this slide, I'm just showing the more general formula that you need to use to calculate the parallel capacitance in case you have many capacitors, potentially a number of capacitors in parallel and with different values. The formula is here. It's very simple. The equivalent parallel capacitance is the sum of all the capacitances of all the capacitors. If you remember, this is the same. This formula is the same. It's very similar to the one used for the series of a resistor. So the resistor and capacitor, very useful thing to remember. The formula that you need to use to calculate the equivalent parallel in series are the opposite. So when the resistors are in series, you need to sum them, while with the capacitors, you sum them when they are in parallel. Whereas when the resistors are in parallel, you have to use that more complicated formula where you have the inverse of the resistor that are summed together, and then you do the inverse of that. And the same strange formula applies for capacitor when they are in series. In this lesson, I want to introduce different types of capacitors. We're going to discuss the main factor that needs to be considered, and we'll compare different capacitors between each other. The goal of the lesson is to allow you to recognize capacitors when you see them on a board and to understand kind of the main characteristics. There are many factors that needs to be considered. We are just going to discuss the most important ones at this point. The first most important factor is the capacitance. Naturally, that's the reason why we have a capacitor in the first place. The second one is the size, geometrical dimension, and volume. This is important because you might not have a lot of space available on the board, like if you're designing a phone, for example. The third is the max voltage / derating. So the max voltage simply indicates what is the maximum voltage at which you can use your capacitor, beyond which you will destroy it, so it's important to know. Derating is a word that is tossed around quite a bit, and what it indicates is that while the capacitor might have a nominal capacitance value, the capacitance is not a constant, but changes depending on the voltage applied or the temperature. So different type of capacitor, in particular the cheapest one, will have a capacitance that is not constant across voltage and temperature. So you have to know that when you design your circuit, so that you take that into consideration. The bullet 4 is the equivalency resistance. So as you certainly imagine, every wire has a certain resistance, so you don't need to have an actual resistor to have a resistance into a circuit. So even the simple terminals of a capacitor will have a certain resistance. So when you add a component to a capacitor to a board, you're not just adding a capacitance to that point, but if you really want to draw the equivalent circuit of that capacitor, it will most likely look like something like this, a resistance in series to a capacitance. The resistance is obviously an undesired effect because it results in a dissipated power, and in general it diminishes the performance of the component. The fifth bullet is the tolerance. This is a straightforward one. So the capacitance is defined as a nominal value, but it's not perfectly defined. You will have a certain uncertainty that's usually determined as provided as a percentage. So when you buy a component, it might be, 10 microfarad, and it's plus minus 20%. So the actual value of the component could be anywhere within plus minus 20% of the nominal value. Finally is the frequency response. We're not going to talk about that now. Frequency response simply is a manifestation of the fact that the component is not represented just by a capacitance, but is represented by a capacitance, a resistance, and also an inductance. So when you see what is the behavior for different speed of the signal applied to it, for different voltages and currents, it will behave much different whether you apply a slow moving current or voltage compared to a fast moving current and voltage. But we are not going to talk about this at this point. There are many types of capacitors available on the market. If you just Google capacitor on Wikipedia, you will find materials for hours. I just want to briefly discuss three main families and the main characteristics. The first is the multi-layer ceramic capacitor, also called MLCCs. These are very, very widely used type of capacitors, probably the most used type. So their main advantage is the small size. If you look at the smallest size of MLCC available, this could be really, really, really tiny. Only a machine can really solder them well. The smallest size could be like 1/4 millimeter by 1/8 millimeter, so really, really tiny. They also have low ESR, which is also a good advantage. Being the size so small, they can keep the ESR small as well. The disadvantages are obviously with the small volume of the capacitor, you have a small capacitance as well. And the other big disadvantage is that they have a high voltage and temperature dependency of the capacitance. So that means that depending on the voltage that you apply, the capacitance might decrease. So they have a certain nominal capacitance as 0 voltage, as 0 bias, but then as you apply a higher voltage, the capacitance decreases a little bit. So you have to keep that into consideration. Finally, these are also the cheapest capacitors. So it's not a surprise that the capacitance, which is sort of the main features of a capacitor, isn't very well controlled and changes with temperature and voltage and such, because at the end of the day, you have a small and cheap component. So you have to pay the price somewhere else. Second type is a film capacitor. So they also have low ESR. The main advantage compared with the and what you see is that they have instead a low voltage and temperature dependency of the capacitance. So the capacitance is pretty stable. They also give you small capacitance, but they have a larger size and usually they're also more expensive. Electrolytic capacitor is another widely used type of capacitor. The main reason to go with electrolytic capacitor is the much larger capacitance values available. They also have low voltage and temperature variation of the capacitance, which is also good. The disadvantages are the high ESR, and given the size and given that the internal structure is pretty complicated, the ESR is quite high, and the size is large, it's pretty large. It's very likely that this will be the biggest component in your circuit. And finally, the most important thing that you have to keep in mind, I don't want to call it disadvantage, just you have to use it correctly, is the fact that these components are polarized, which means that their orientation is not arbitrary. There is a negative terminal and a positive terminal, and you have to make sure that the voltage is always oriented in that direction, otherwise you will break the component. You can see from the picture that usually the negative terminal is the one that is indicated, like this. You see the negative terminal, or this little dot, or this little band. So you always have to make sure to use them with the right orientation. Besides that, is the components that gives you the highest value for capacitance. Usually your circuit that you're going to design is going to use a mix of different type of capacitor, because each of these will have a different application where they're best compared to the others. So and most likely your circuit will almost always contain a mix of electrolytic capacitors and multi-layer ceramic capacitors.